very much for having me here. I'm very happy to visit Neurospin for the first time. So thank you for the invitation. And not just because this is Holly and my first double-header talk, but also I'd like to try to convince you of the feasibility of localizing layer-specific neural activity with MEG. It's a big claim, I know. Bear with me. So why should we even care about cortical layers? So it's now well known that at least in the visual system, cortical regions form a hierarchy with feed-forward and feedback projections, and that levels in this hierarchy can be distinguished by laminar asymmetry in their connections. It also appears that oscillatory activity is laminarly organized, with activity at low and high frequencies predominating at different cortical depths. And modern computational theories, such as predictive coding, and more general top-down, bottom-up accounts ascribe mechanistic roles to frequency-specific activity in deep and superficial cortical layers. That would be great if we could test these theories non-invasively in the human brain. And MEG is an attractive technique for this because it's a direct measure of neural activity, it's non-invasive, it covers the whole brain, and it has excellent temporal resolution. So in the last 6 years or so, me and my collaborators have developed several techniques for performing laminar inference on MEG signals. And the first, the simplest, involves comparing forward models based on peel and white matter surfaces representing superficial and deep layers in terms of model evidence. So the idea here is that you fit two models to the same data, one assuming that all the activity is happening in the superficial layers, and one assuming that it's all happening in the deep layers. And this comparison can be done using free energy as a model evidence metric. Now, this is a parametric measure that captures the trade-off between accuracy and complexity. So the model has to be accurate enough to explain the data, but not so complicated that it's overfitting the data. You can also do this using cross-validation error, which is a non-parametric measure. And we've shown that these two metrics are highly correlated. So if you don't like free energy, that's okay. Now, we could also do this model comparison using a spatial prior in a sliding time window to get some spatial and temporal specificity. So here, this is showing we do this free energy model comparison within a short time window of our MEG signal. And then as we slide that window along, we can plot the relative free energy for our peel and white matter surfaces. So for our superficial and deep layer models. And so you can see whenever it's peel minus white. So when it's negative, there's more model evidence for the deep layer activity. And where it's positive, there's more model evidence for the superficial layer activity. And so we use this to test some of Stephanie Jones's models of beta bursts being driven by a combination of deep and superficial layer synaptic drives. And we found good evidence in support of this model that also matches what we've seen with more invasive recordings in rodents and monkeys. We also developed an ROI analysis, and this involves a forward model that combines both surfaces, right? So now your forward model actually has two subsurfaces within it, like a sandwich. And then what we can do is compare directly the source level activity within corresponding locations from each of these models. And we use this to show that high frequency neural activity predominates in superficial layers and low frequency in deep layers. And again, this is in agreement with what's been found in invasive intracranial recordings in monkeys. Now, there are several requirements for performing these analyses. So high resolution MRI, we need to be able to extract really nice surfaces. MEG data using headcasts to reduce co-registration error and within session movement. And so you can see here, this is the new generation of headcasts that we're designing that are 3D printed using a flexible TPU material with a sort of mesh, tessellated mesh design, which improves airflow and so increases comfort. And it also involves lots of custom code for cortical surface processing and source reconstruction until now. And I'll say some more about that later. So what I want to talk about today is our recent efforts to extend this deep versus superficial comparison to the full range of cortical depth. What we're aiming for here is true laminar resolution. So first, we need a multi-layer forward model to constrain source reconstruction using anatomical priors. So to construct this forward model, we first extract the peel and white matter surfaces, the boundaries from high-resolution MRI volumes. We then generate 9 equidistant surfaces between the white matter and peel surface, resulting in 11 surfaces total. And these will define the dipole locations of our source space. We downsample these surfaces using a custom method together to maintain their vertex correspondence across layers. So each vertex on the peel surface has a corresponding vertex in each of the other surfaces. And we constrain dipole orientation using link vectors. So vectors connecting these corresponding vertices. Right, so now we've got a forward model that encapsulates all of these anatomical priors in terms of the location of where our dipoles could be and their orientation. So these 11 surface layers are not meant to directly represent lamina, but to sample them evenly, like a laminar electrode with equally spaced contacts. And now we can fit forward models based on each surface layer to the same data and compare the model evidence for each of them. Now we wanted to first test this approach in simulation. So we simulated activity in each surface layer, generated a synthetic sensor-level data set using a multi-layer forward model, and then for each laminar simulation, we compare the model evidence for each of our forward models. And ideally, the model corresponding to the depth of the simulated activity should have the highest model evidence. And so, does this work? There we go. All right. So this blue line here, this really light blue line, is showing the model evidence for each of our 11 surface layer forward models for a simulation that was run with activity simulated at the peel surface. Yeah, and you can see the highest model evidence is the peel surface model. And then here's one for the next surface down, all the way down to the white matter. And so we can summarize this in a matrix. So here you can see just these same data plotted in a matrix. So each column here is a simulation, and each row is an evaluation layer. And so if laminar reconstruction is perfect, what we should see is that along the diagonal is where we have the highest model evidence. And so from this matrix, then we can compute the error, right? We could compute the distance from the peak to the ideal location. And we can compute the bias, so whether or not there's any bias towards the superficial or the deep layer sources. So we first went about simulating activity in each layer at 100 random cortical locations, and we varied the SNR of the simulated data set from negative infinity, so pure noise, to 5 decibels. And so here's what those matrices look like. So at negative infinity, basically the peaks are anywhere, random. But as the SNR increases, you can see that matrix becomes more and more diagonalized. And so this is showing the mean model evidence over all of our simulations, and this is showing a probability density map of where the peak is. And so you can see between negative 50 decibels and negative 35 decibels, it becomes more diagonalized. By negative 20 decibels, it's pretty perfect. And so just to summarize all of that, what we found is we compared this with a permutation-based approach where we shuffled these matrices and computed the expected error in terms of layers that you would expect by chance. And we found that once you get to negative 50 decibels, really negative 35 decibels, laminar inference was more accurate than you would expect by chance. Okay, so those simulations were just varying the SNR of the signal, but didn't have any simulated movement or co-registration error. So we ran another set of simulations, this time varying the co-registration error. And so you can see here what that looks like. Again, here, this is 0, this is perfect co-registration, and you can see this matrix start to degrade, as the simulated co-registration error increases. And so again, with the permutation test, we found that the co-registration error has to be less than 2 millimeters for accurate laminar inference. But importantly, these SNR and co-registration limits are within the range of what we can achieve with headcast MEG. So far, so good. But even under the ideal conditions, anatomical factors could influence the accuracy of laminar inference across the cortex. So now we ran these simulations with negative 20 decibels SNR, 0 co-registration error over the entire cortex of one person's brain. That's about 29,000 vertices per layer, about 300,000 simulations total, and we completely exceeded our allocation on our local computing cluster. And we found that under these conditions, laminar inference was perfect in 85% of the locations, but there were regional variations. So we then tried to relate laminar inference error to anatomical features like the difference in the lead fields between the deep and superficial vertices, dipole orientation, distance to the scalp, and cortical thickness. So we found that indeed anatomical features could significantly predict laminar inference errors. So what we're showing here, each of these plots is showing orientation, distance to the scalp, and cortical thickness related to the lead field difference between the deep and superficial layers. And they're color-coded according to the error at that particular location. And then what we did was we found, so you can see the marginal densities here on the sides and the top, and we tried to find, boundaries that maximized the area under the curve. So in an ROC analysis to separate out vertices where there were no errors to vertices where there were. And so particularly what we found is that lower lead field separation, thinner cortex, greater scalp cortex distance, and more tangential orientations predicted higher error. And we also ran a multivariate logistic regression, and we found that the lead field difference was actually the strongest predictor of error, followed by orientation and cortical thickness. And this is pretty much what you'd expect, because the lead fields incorporate all of these other factors, right? That all that information is there in the lead field matrix. Right, so that was all in simulation, but what do we do with real data? So our intermediate surfaces, as I said, they give us something like a virtual depth electrode with 11 contacts. But we'd like some way to determine the actual approximate layer boundaries. And so for this, we use the Big Brain Atlas, which is an ultra-high resolution 3D histological atlas of a single human brain. And Konrad Vogtstuhl has trained a convolutional neural network on this atlas to segment cortical layers and create a map of layer boundaries over the whole brain. And we take advantage of this by using the Big Brain Warp toolbox to map this relative layer thickness atlas to each subject's brain. And this gives us then a rough estimate of which cortical layer, which lamina, each of our virtual depth electrode contacts is in. And so here's just a sneak peek at some preliminary results from applying this analysis to adult MEG data, specifically visual and sensory motor event-related fields. So we found that we were able to demonstrate layer 4 responses about the time that you would expect them, here and here, in the visual and in somatosensory cortex. This is right after a button press. This is right after the presentation in the same experiment of 2 different visual stimuli. And we also found strong layer 5 activity just before the button press in motor cortex. So we're now looking at how these signals are modulated by visual and sensory motor predictions and prediction errors. And hopefully in a few months, I'll be back and telling you how that went. However, this approach isn't perfect yet. So as I've shown you, when we simulate a single source under ideal conditions, laminar inference is perfect, right? At each of our layers, we're able to identify which layer that came from. But if we simulate 2 simultaneous sources of equal strength, and so in this set of simulations, one source was always simulated in the middle layer, and then we simulated another source gradually getting closer and closer to it, or moving farther away. And what we found is that using this, the winning surface layer model was the one in between the 2 actual sources. Yeah. So it's not so bad, because this is not actually a biologically plausible situation, right, where you have 2 sources of exactly equal strength happening at the same time. And if we look at the model evidence across simulation layers, and across evaluation layers, we can see that there's still some difference compared to the single source simulations. So this suggests that using some kind of more refined approach like Bayesian model averaging rather than the current winner-take-all approach might be able to improve the discriminability here. Now, I mentioned at the beginning that we constrain the dipole orientations using link vectors as an approximation of cortical column orientation. But there are several methods for estimating cortical column orientation from MRI-derived surfaces. So link vectors is here in black. You can also use surface normal vectors from the original surface. You can use cortical patch statistics, the surface normal vectors from the downsampled surface. Actually, that's the default in SPM. But each of these methods really differ from each other by up to 30 degrees, which I was really surprised to find out. So we ran another set of simulations, and this time we simulated activity using one method, and we performed laminar inference using forward models based on each of the other methods. And we found that the dipole orientation had a large impact on laminar inference accuracy. So here you can see, this is each of our simulations. This is the difference between the true simulated dipole orientation and the dipole orientation used in the forward model for source reconstruction. And you can see that as that difference increases, your laminar inference error increases as well. So the method relies on accurate estimation of cortical column orientation, which currently I think is not possible using MRI, but there may be some promising approaches using diffusion-weighted imaging to provide this. So I mentioned at the beginning as well that all of these analyses involved a lot of custom code until now. So I'm really pleased to announce laMEG. It's French, laMEG. I'm assured that magnetoencephalography is female. Is that right? I hope. Doesn't work otherwise, laMEG. So this is a Python-based software package that provides support for performing laminar simulations, as well as multiple types of laminar analyses with real MEG data. So based on model comparison using free energy or cross-validation error, the sliding time window approach, the ROI-based analysis of frequency-specific power, and an experimental CSD-like analysis. It's simple to install, and we've been working on making it easy to use. And we've extended each of these analyses to work with any number of intermediate surfaces. So here are some example results for a single location. So we have the free energy analysis, cross-validation error, and here we want the lowest cross-validation error, right, rather than the highest free energy. The sliding time window analysis, and the ROI power analysis. And laMEG includes example code and tutorial Jupyter notebooks for demonstrating each of these approaches, both in simulation and applied to real data. So maybe I haven't convinced you that laminar MEG is real or even worth doing. But even so, you should still check out laMEG, because as a bonus, you get SPM compiled as a Python library, which allows you to interact with it via Jupyter notebooks, including visualization. And this includes automatic installation of the MATLAB runtime environment, which means that you don't need a MATLAB license, and you can run massively parallel simulations and analyses on a large computing cluster and get your IT department upset with you like mine is. I've shared these developments with the SPM team, and they should be coming out with a complete Python version of SPM sometime by the end of this month. So Holly didn't have time to talk about this, and neither do I really, but she ran these simulations using infant MRI and MEG data with varying levels of SNR and co-registration error to establish the feasibility of laminar infant MEG. And this was done using some infant MEG data collected by Sophie Pouton and some high-quality infant MRI data that we collected in Lyon. And she's shown that with high-resolution MRI, including online movement compensation, so we use a track-aligned system to do online movement correction with the MRI, flexible infant head casts, and max filter movement compensation for the MEG data, it's possible to achieve the levels of SNR and co-registration error necessary to infer the laminar origins of signals in the infant brain. So where do we go from here? The analyses that I talked about rely on model comparison. But if we do source reconstruction on an 11-layer surface mesh, we could estimate source activity at each layer and use a current source density-like analysis. And this is obviously very challenging, so we're taking a computational model-based approach to establish its feasibility. So we're using the human neocortical neural solver to fit canonical biophysical models of cortical columns to event-related fields from real MEG data. And then we can simulate laminar recording from a multi-contact shank with the model and run these laminar signals through our multi-layer forward model to generate synthetic sensor-level MEG datasets. And we can then test our experimental CSD-like analyses on these synthetic datasets and compare the results with the same approach applied to real data. And so far, it looks pretty promising. And finally, I often used to wonder, or worry actually, about the impending shift towards OPMs. So would these analyses still work? How many sensors would be needed? How close to the head would they have to be? And I'm no longer so worried because Saskia Helbling at the Ernst Strungman Institute was recently able to replicate my laminar simulations, which was a huge relief. But she also extended them to simulate different OPM sensor arrays. And so check out her paper, and this functionality will soon be integrated into laMEG. Okay, so I hope that I've shown you that at least under the right conditions, it's possible to perform non-invasive resolution of cortical activity at laminar depth with MEG. We found that reliable laminar inference could be done with SNR, well, about -35 decibels, -20 is better, with a co-registration accuracy of less than 2 millimeters. We found that anatomical factors influence this precision. With real data, we've shown laminar-specific activity that's consistent with invasive neurophysiology. Our current challenges involve resolving simultaneous sources of equal strength and estimating cortical column orientation from each subject's MRI. In our future directions, we want to integrate this with computational modeling using the human neocortical neural solver, apply these to OPM sensor arrays, and we've currently got a few projects planned to compare these with intracranial recordings, intracranial laminar recordings in human patients. So like I said, this is the result of work by many people over the past 6 years or so. And so I'd like to thank all my lab members and collaborators who have contributed, as well as our funders. And I'd like to invite you to give laMEG a try, join our development community, and enjoy laminar inference with MEG. Thank you very much.